Just a review of what we did last lesson, or actually what you've seen on the videos that I sent you. We're just looking at sketching things like modulus of z. Remember, modulus of z means the distance of all points in the plane that are r units from the origin. So modulus of z equals 2 would be a circle with centre 0, 0. So a circle with centre 0, 0, radius 2. Modulus of z less than or equal to 2 would be a solid line circle, and it's the points that are within 2 units from the origin. So you'd shade inside the circle. With this one here, actually I've got to fix this. Do you know what I've done wrong? With number 3? Yeah, one of them's a dotted line. Did I say that in the... Yeah, so one of those I must not have had... the dotted line, the one-on-one should be a dotted line. So we need a dotted line on the inner circle. So basically the modulus of z lies between 2 circles. And the first circle, see, we're sketching modulus of z equals 1, and we're sketching modulus of z equals 2. And you shade in between, but the modulus of z is greater than 1, so the inner circle is dotted, okay? So then we also looked at this second type. So when you see this second type, modulus of z is 1 minus, see, these have to be in this format, z minus z1. You would sketch z minus z1 equals 4, for example. I'll do it from this one. One sec. Wait a sec, I'll do it over here. I've got it here. So this is just having a quick look at what we did, because in today's lesson we need to know these as well. So this has to be of the format z minus z1 you draw equals r, the radius or whatever of your circle, but it's the distance of z from z1. So first you sketch 1 plus I, which is the point 1, 1 on the Argand plane, and then you need a radius of 4 units from there. So you'd go up 4 units, across 4 units, down 4 units, across 4 units. It would be a dotted circle as well, and it's the region inside the circle, okay? Then this, if you see this one here, for example, written z plus 2 minus 2i, you've got to change the way it looks, because it must be of the form z minus z1 equals the radius, which is why we've rearranged this as z minus negative 2 plus 2i, okay, because you get plus 2 minus 2i, etc. So you need a circle with centre negative 2, 2, radius 2. You'd go 2 units up, down, sideways, etc. Now, we also worked out minimum and maximum distances and all that. Then you may see something like this. So this is another type. So this is the third type that we've seen. The third type is where you've got this. Z minus Z1, modulus of Z minus Z1 equals the modulus of Z minus Z2. See? Z minus this complex number equals the modulus of Z minus the other complex number. It is the perpendicular bisector of those 2 points. Yeah, so it's the perpendicular bisector of the line joining those 2 points, okay? And to do that, you would do it geometrically. So here, this has been written as z minus 0. This is z minus this complex number. You put the point 0 on the complex plane, and you put negative 1 root 3 on the complex plane. And you're basically looking for the midpoint of those two. You're looking for the gradient of those two. Then the perpendicular bisector, you'll do the negative reciprocal of the gradient to find the gradient of this, and then you'll use the point gradient formula. So doing this type is just like geometry, you know, linear function topic, where you're just finding the perpendicular bisector of the line joining 0 and A. You want the perpendicular bisector of that, which is BC here. So it's just done using properties of geometry. You can also do it by substituting x plus yi for your complex number, so I've done it algebraically as well. And same with this one, it would be the perpendicular bisector, making sure you write it as z minus z1 modulus equals modulus of z minus z2. Again, plotting those points and doing the perpendicular bisector of those, and then we also looked at the minimum value. So that's all in that video. Now, I think this is where we're up to. Is that right? Type 4. So I've already done these. I can go to a blank page and do them all again. So we've got type 4. We're up to page 42. And, yeah, I'll just go here. Or do you want the solutions up and I'll just talk through them? So type 4. You may see something like arg z equals some angle. Now, arg z, remember, is the angle that you make with the positive direction of the x-axis. With not the positive direction, with the positive real axis. It could be upwards or it could be downwards. Reason is that arg z, you know, lies from 0 to pi and from 0 to minus pi. You know, remember that? So arg z runs from negative pi to pi. Remember, you can't have like 2 pi. You can't have 3 pi on 2. Can't have that. So RZ can be positive this way or negative that way. Okay? Now, that would be a positive theta and this would be a negative theta. All the way up to pi. Up to negative pi, sorry. There. Now, sorry, I'm off screen. Now. You're allowed to have arg z equal to pi. Oh, yeah, I suppose you'd call it positive. Yeah, you'd call it positive. Okay? All right, now, sketch the locus of the following. Arg z is pi and 3. That's just, isn't it 60 degrees roughly? All right, my line isn't looking like 60. If you could, my ray, I mean, if you could make it a little bit higher, that would be good. Make it look like 60 degrees, okay? So, the main thing here is that arg, we're not dealing with complex number equal to 0, so arg 0 is undefined. So whenever you draw these rays, we need a circle at the beginning of your ray, okay? So what it is arg z is the angle made with the positive direction of the real axis, okay, by the vector from the point representing z. This is really important. There is an open circle at the origin. If you've got complex number equals 0, you're not sketching anything. So you just need to learn that arg 0 is undefined. Okay? So if you want to sketch arg z equals pi and 3, you're just doing the ray from the origin to, I'll just put it to whatever point. You can call it point A, but I'll just call it z. And you've got pi on 3 is an anti-clockwise angle of pi on 3. In the second one, we've got to draw two things. We need to draw the angle minus pi on 4, and that goes this way, 45 degrees. And then this one, obviously, everyone, needs to be bigger, so needs to be 60. So you really need to show that this is higher up than that. That should be really like y equals minus x down here, halfway between, all right? This needs to be at a, more than halfway, make it about 60 degrees. This one needs to be a solid line. This one needs to be a dotted line. Okay, just going back, sorry. If we think of arg of z as arg of z minus 0, when we come to this type here, and if you think of it like that the vector goes from 0 to z. If you look at this type, type 5, arg of z minus z1 is theta. We have to look at it as the angle, the vector, from the point z1 to the point z. So we're going from z1 to z. So let's say z1 is here and z's there. The vector goes from z1 to z. So also, again, there's an open circle at z1 because arg 0 is undefined. So if we look at this first example here, arg of z minus 2 plus 2i equals 3 pi and 4. This needs to be in the form of arg z minus z1. Okay? So that's why we're writing it as arg of z minus 2 minus 2i. Are we okay with this? Equals 3 pi and 4. So what we do, actually, do you prefer it like this or do you want me to do it on a blank and rewrite it? I'm happy to start on a blank. If it's less, I will. So here we go. And I'll just have that one here. So we've got, this needs to be in the format of arg z minus 2, z minus z1, which is z minus 2 minus 2i, is 3 pi and 4. Right. They're allowed. All right. Okay. So it's the vector from 2 minus 2i to z. And the angle has to be 3 pi and 4. So where's 2 minus 2i? 1, 2, minus 2i. That's where it is. Now we just write it as the point 2 minus 2 on the plane. Now, if I put that angle out here, remember the angle has to be the angle it makes with the, let's just pretend we're up here. How do you get 3 pi and 4? Don't you go like that? Isn't the direction that way? Do you see that? So, now, wait a sec. This needs to be drawn accurately. Tell me what 3 pi and 4 is. If I draw 3 pi and 4 like that, this is 45 over here. Look where this point is. This is really important. This is 2 across, 2 down. Tell me about this angle. 45. So if I want, so I'm just going to draw it in for you because it goes like this. Because I need I'm going to put a dotted line here. From there, my angle's got to be 3 pi on 4, 135 degrees, which means it's 45 here. Because this is 2 across and 2 down, this is automatically a 45-degree angle in there. Do you see that? So therefore, the angle there is 3 pi and 4. Now, I don't write my 3 pi and 4 there. What I do, I start here and I work out the direction of 3 pi and 4. I put a little dotted line here in my head. And then I go 3 pi and 4. But I know it's got to pass through 0, 0 because that's a 45-degree angle. Because the gradient of this line is -1. So, see, a thing like this is really important to show that it does go through the origin. Because, look, that's 45 degrees there. Because that's 2 across, 2 down. You've got an isosceles triangle. So, therefore, I show the 3 pi and 4 up here when it actually crosses the x-axis. But look, I could show it down there, but you're sort of losing your diagram of your vector if you do that. Remember, this line is parallel to the x-axis. My dotted line that I put down there, that is parallel to the x-axis. From there, I know the direction that I'm supposed to draw it in, right? Because 3 pi and 4 there, I've got 45 degrees here. I know that this is a gradient of 1. I know that it's got to go through the origin. Are we sure about that? All right. So that's my vector. So that's Z1, which is there. This is Z. Remember, the vector gets drawn from Z1 to Z. You know, like with your circles, modulus of Z minus Z1 equals the radius. The center of the circle was at Z1. So with all these types, you start at Z1. So you've got to locate the point Z1. When we did modulus of Z minus Z1 is the radius, the center of our circle was Z1. Now this is the beginning of our vector at Z1. Okay? So now, so I'm just going to write a few notes here. So we want this to be in the format of arg Z minus Z1 is theta. Z1 is the fixed complex number. So Z1 is the fixed complex number. I can call it A if I want, it doesn't matter. I'll call it A, which is 2 minus 2i. If I everyone, what you'll notice sometimes is that they won't write Z1 and Z. They'll call this point A and they might call this point P or something, that P lies along this line. All right, if I let P represent Z, then I can have vector AP. Do you know what I mean? Vector AP, therefore, is Z minus Z1. So I don't have to write Z1 there and Z. I can write it as vector AP represents Z minus Z1 because Z minus Z1 is the vector from Z1 to Z. Okay? And we know that vector AP makes an angle of 3 pi on 4 with the real x-axis, with the positive direction, with the positive real axis. Doesn't have to be in the positive, doesn't have to go positive angle. As long as it's with the positive real axis, it means I don't start my angles on the negative real axis. The angles start on the positive real axis. Just note, we've got an open circle, just a few things to note. Open circle at 2 minus 2, as the reason arg0 is undefined. Okay? Now, we'll go to the next page. In this one, it already is in the format of z minus z1, okay? z1 is your fixed number. So this already is in the format of arg of z, z minus z1 equals theta. Remember where z1 is your fixed complex number. If we want to draw it as a and p, we can let a represent our first complex number, 1 plus 2i, and you can let p represent or represent z. So let a be your complex number, let p represent z. Therefore, your vector AP will represent z minus z1. Okay? So let's draw. We've got 1 plus 2i is up here. So you can just write it as 1, 2. It can be the point A. Remember, the vector goes from z1 to z. Now, you can have a little sketch over here if you want. Where is minus pi on 3? How do you draw it if I'm starting from here? Down. How many degrees? All right. So your vector, I need an open circle there, and the vector's got to go down 60 degrees. So see, this is pi on 3. So I need your vector going in that direction. But you don't write the pi on 3 up here, you write it down here. Is that all right? So once you've cut the x-axis, that's where you write your pi on 3. You show it down there. Now, I don't have to write minus pi on 3. The fact that it's going downwards tells me it's minus pi on 3. Does that, got the idea? Okay. Now it has to go that way. I don't do it. Why don't I do it the other way? Because the vector's not pointing upwards. I need to, so the vector goes from there to z in that direction of minus pi on 3. So it's got to go down that way. So it's the angle that the vector makes with the real x-axis, which is this. All right? It's really important that you got that vector going the right way. Okay, so AP represents z minus z1. Okay, so we know that AP makes an angle of negative 60, makes an angle of minus pi on 3 with the positive real axis. Not in the positive direction, it's actually going in the negative direction, but it's with the positive real axis. This is the positive real axis. Okay, remember, open circle at A as arg of 0 is undefined. Got it? Goes like that. Okay, the next one. We all right? Arg of z minus 1 plus 2i looks same beginning spot, 1 plus 2i, open circle, 1 plus 2i. Oops, we just go 1 comma 2. Do you need your thing? So this is, okay, we've got A, it's the point 1, 2 again, but that angle needs to be making, I'm just going to do my pi on 6. I think it's a good idea to do your other little diagram down on the side. If I do positive pi on 6, which way does it go? Up. Yeah, up. How much? What's pi on 6? About 30 degrees, so make sure it doesn't look more than halfway. So we got pi on 6. So from your point, just do the same, you know, pretend you've got a little dotted line there. We need a 30-degree angle up there. So obviously I need to put these points somewhere else. They're all in the way. So I've got an open circle there. I'll need a, well, what we can do is I'm going to do a dotted line down here so that if that were to continue, I can go that this is A, which is 1, 2. This is my vector, the solid line, but the angle that it makes with the axis is pi on 6, sorry. Let me just fix this. So if I continue that, and you want it, the angle that it makes with the positive real axis is pi on 6, but that's actually not the vector down there. It's the same as putting the pi on 6 here, all right? All right, it looks a bit crooked. But sometimes you'll see the angle, they often show the angle on the x-axis. And I know this happens to cut at the negative numbers, but it's still, the angle is made with the positive real axis. It's made with, in other words, it's not coming up from this side. It's coming up or down from there. Not that way. I don't want any angles drawn from there. So I don't want an angle written in here. No. I don't want an angle written in there. No. It's got to be up or down from the positive real axis. Okay? So therefore, if that's A, this could be P. Okay, so again, there is a circle at A. So A is excluded. All right? Now, the next one. Now this is a combination of what was in the video from last week and what we've been doing today. So we've got two arguments and we've got modulus of z less than 2, which means a circle with radius, what? Centre, 0, 0, and or does not mean intersection of. It means I want that region shaded and this region shaded. That's what or means, okay? If it said and, I want the union, okay? So, oops. So I need both of those regions shaded. So what do we got? Arg of, what's the first one? What's pi on 4? 45. Okay, so we've got a 45-degree angle. And then we've got, what's pi on 2? 90. And that. And it looks like we've got shading between them, doesn't it? Arg of z lies between them. Here's pi on 4, and there's pi on 2. That angle up there is pi on 2. So therefore the shading looks like it's between them. We also want, so I'm going to draw that as just a vector. Now, I can have an open circle at the moment, but I'm going to colour it in a minute because we've also got circle with radius 2 and everything inside it coloured in. Dotted line but. Which is why I do not have an open circle anymore at 2. Because when I come to shade the inside of the circle, I colour in the origin. Because I want the union of them. Not the union, I want them both. So if you're just shading modulus of z is less than 2, you don't leave an open circle at the origin. So I want both of them shaded. So the modulus of z less than 2 includes the origin. Even though the other one doesn't, but because I'm shading them both, if I want the union of the two of them, all right, actually we'll do it over here. Let's say I don't want or, let's say I want pi on 4 less than or equal to arg z less than or equal to pi on 2 and so I want the intersection of, so like this, intersection of or and, or this. Or I can say shade the region satisfied by both these inequalities. And modulus of z less than 2. If I asked you that and shade the region satisfied by them both, I would do my dotted circle, but where would I shade? And what would I leave open? I think I'd just do this. Union. The intersection of the two.
Wait, doesn't that mean you have to...
I don't go out here.
For that graph,
2, I'm looking now at this circle.
But you also have to...
shade it in.
Not shade it, make it a solid line.
This is solid. Yeah, that's solid. That's solid. This is not.
No, for that other question.
All right, just one sec. Yeah. But the shading, yeah. That's now included, but the shading shows that it's included. Yeah. That's good. So, you know what, but the shading will take care of that anyway. Do you know what I mean? Now this one, actually, z is less than 2 units from the origin. Do we include 0? Oh, but it's the intersection of them both. It's all the points that hold for both. you open the circle. Okay, you open the circle if I ask you that way, if I want the intersection of these regions. Got it? So you'd have an open circle on the other one. Okay? All good? So that one's OR, the first one. And the intersection of the regions does not include the origin. You've got solid lines on the pi on 4, and you need to show pi on 4 here. And you'd probably want to show that that's pi on 4 inside there as well. But, yeah. Okay? All good? Okay. Can I? Okay. The next one. Arg of z minus 2i over z plus 3 is 0. When you do the arg of something over something else, what's the rule? What do you do with the arguments? Subtract. So we've got, that is the same. So the arg of, so using the fact that arg of z1 over z2 equals arg of z1 minus arg of z2, we're going to do this. So therefore, we've got that the arg of z minus 2i over z plus 3 is the same as, actually I shouldn't have written that again, but it doesn't matter, arg of z minus 2i minus arg of z plus 3. So therefore that over that is the same as that, which equals 0. Can I write that? So therefore, just ignoring this first bit, therefore we can say that arg of z minus 2i is equal to arg of z plus 3. So I'm just taking this arg of z plus 3 over the other side. Now, what that means is that what does arg of z minus 2i mean? It means find where minus 2i is and draw, it's the vector from 2i to z. And arg of z plus 3 is the vector from negative 3, I'm going to rewrite that out. So therefore, this is the same as arg of z minus 2i equals the arg of z minus negative 3. Because it's got to be in the format of arg z minus, z minus. So now I'm going to do a sketch. Oh, I'm going to need some room. I think I'll do the sketch over here. So we've got this. We've got negative 3. And we've got 2i up here. Now, we have to put circles around them because the arg of 0 is undefined. Okay. Now, what have I done there? Oh, okay. So now, what we've got, one sec. 1, it's the vector from, it means the direction of z from 2i is the same as the direction that, remember the arg is the angle that your vector makes with the real axis. So the angle that the vector makes from 2i is the same as the angle that the vector makes with minus 3. Got it? That's what that means. If the argument of the first one equals the argument of the second one, it means that the angle that those vectors make, that you're going to draw, make the same angle with the real axis. Because remember, arg of z minus z1 often is equal to theta. So arg of z minus z1 will be some angle, and the arg of z minus 2i will be some angle, and the arg of z minus, or z plus 3 is another angle, but the angle happens to be the same because the two args are equal to each other. So what we do, just watch what I'm going to do. I'm going to draw a line between them, but I'm just going to dot it at the moment because I don't know exactly where I'm shading. Well, I'm not sure where I'm going to make the line solid. All I know is that the argument of each of those vectors are the same. Now, I've got to decide now. So what I'll do, I'll just write a little sentence here. Okay, so we've got the angle of inclination, which is the angle from the real x-axis. So the angle of inclination of vector from 2i to z equals the angle of inclination of the vector from negative 3 to z. So therefore, z is along the straight line joining 2i and -3. Now we've got to decide where is z on the line. Now, just listening really carefully. What if I put z in the middle? Well, then that vector goes that way and the other vector goes the other way. That means that the angle of inclination is not the same. Because if I've got a vector going this way, the angle of inclination is there, right? If I've got a vector going that way, the angle of inclination is just that. So z does not lie between those 2 points. Z therefore has to lie on one side of those points. So therefore Z, or point P, or whatever I'm going to call it point P, lies outside. Okay, so what I'm going to do, I'm going to put this, I'm going to let A be the point, be that complex number 2i. What do I call it? 0, 2i, or the complex number 2i. I'm going to let B be the complex number, what is it, -3, 0. Okay? Now, that means, see, AP goes that way. Well, so does BP goes that way. So Z has to lie out here, or it could actually lie down there. So Z is either, or point P is either up here or it's down there, but not both. So look, AP's direction is that way, and so is BP's direction. So therefore P, or the vector Z, has to lie not between A and B. Because if it lies between, watch, so P is vector Z, right? If P lies here, isn't AP that way and BP the opposite way? So if they're in opposite directions, they've got different arguments. They have to be the same vector in the same direction to have the same argument. So therefore, P, if I put it up here, AP's like that, and so is BP. And if, you know what, if P's down here, BP's like that, and so is AP. So what we want to put is, so therefore, Z must be on, so you can also put the arrow down here as well, but only just put P on one side. So this is what I want. I want a solid line with an arrow going up there and a solid line with an arrow going down there, but just put P on one of the sides, because P is either going to be on one side or the other. So Z must be on the outer parts of the line. Now, therefore, AP, the vector AP, will have the same direction as the vector BP if Z or P is on the outer part. Does that make sense? Because if you put it in the middle, you can clearly see, if you're doing the angle from the real x-axis, that one of them's like that and the other one's like that. Now this other one is, so that's where you've got arg of Z minus Z1 over Z plus Z2, or minus Z2 equals 0. You take one of the arguments to the other side and you say that the direction for those two vectors is the same. Okay? Now you've got the next type. Arg of Z minus 2i over Z plus 3 equals pi. So again, it's the same points. So let's just write down what this means. Doesn't this mean that the arg of Z minus 2i, how do I write that? Minus, doesn't this mean, yeah, so the arg of Z1 on Z2 is the arg of Z1 minus Z2 over the arg of Z plus 3 equals pi. Now, you know pi? What's pi? 180. Pi is there. In other words, those two vectors are in opposite directions. Or I can do, if I take this minus arg Z plus 3 to the other side, it's like saying arg of Z minus 2i equals pi plus arg of Z plus 3. So when one argument minus the other equals pi, it's like you've got, watch, that minus that. Is that right? So if I do that minus that, what do you get? Does that give me the opposite? Yeah, I know. I'm just trying to... You know what? If I take that over, then one argument will be 180 plus the other argument, pi plus the other argument. In other words, you take the argument of the first one and rotate it 180 degrees and you'll get the argument of the second one. Do you want me to, so if I write it as that, arg of z minus 2i equals pi plus the arg of z plus 3. So therefore, the first argument of z minus 2i is 180 degree rotation of the other one. Does that make sense? Therefore, so what we'll say, therefore the direction from, remember arg of z minus 2i is the direction from 2i to z is exactly opposite to the direction of minus 3 to z. So you know how in our first diagram, z had to be on the outside? If they're in exact opposite directions, same question, the z or p lies between a and b, that's all. So notice it's almost the same as the first question. Look, z minus 2i over z plus 3 equals 0. If you've got that, the point's on the outside because AP and BP have to be in the same direction. This one I've got exactly the same points, but one's the opposite direction to the other, the exact opposite. So therefore, the point P lies between A and B in this case. Okay? So here we've got, so let's draw it. We've got minus 3 and 2i, circles. So therefore, P, if I call that point A, and this is point B, notice that AP goes that way. Do you know what I mean? And BP goes that way. So if I call A point 2i and B is the point negative 3, 0. So if A is 0, 2 and B is negative 3, 0, then AP is the opposite direction, is the exact opposite direction, or has the exact opposite direction to BP. So therefore P lies between A and B. Okay? So so therefore Z is anywhere along the inner part of the straight line joining 2i and negative 3. In other words, AP and BP are in exact opposite directions, or they're in opposite directions. Got it? Okay. Now, question 9. There's a few more to go. Oh, and there's a mistake in this question. This is arg of z plus I, arg of z minus 1. Please fix it. That's a 1, not an I. So arg of z plus I equals arg of z minus 1. So let's draw what that means. Doesn't this mean that the vector from I to z equals the same direction, has the same direction as the vector from 1 to z? Because it's got to be arg of z plus I equals arg of z minus 1. This is the same as the arg of z minus negative I. I think I've just said the wrong thing on video. So let's go. I think I just did. So let me just draw it. Because z plus I is at negative I. Just got to draw it. Open. Oh, that's not negative I. That's negative 1. Negative I is down here. And 1 is here. Actually, I need to make it bigger. Right, let me just make this all a whole lot bigger. Sorry. We just need to see. Now, I'm not sure which way it's going. Put some circles at 1. So arg of z minus 1 here. I'm not drawing the arg yet because I don't know what it is. And arg of z minus negative I. If the direction is the same, does the point P go in the middle? Just think if P's in here, yeah, it goes outside, good. So you do solid lines on the outside. Now I'm just going to put the point P up there, but it could be down there. It's either up there or down there. Okay, I'll call this one point A. I'll call this point B, and I'll just write up here. If A represents or is the complex number negative I, and if B is 1, 0, so I'll write 0. I better put 0, negative I, or negative 1. It doesn't matter. I'll just write A is negative I. That's the complex number. Oh, yeah, I do too. Okay, I'm just going to, can I swap them down here? I'm going to call this one A, this one B. So if A represents the complex number negative I, and if B is the point 1, 0, P is going to be my complex number Z, then AP, the vector AP, doesn't AP represent APZ plus I? Because it's the direction from minus I to Z. And BP represents the vector Z minus 1. Because remember, the way it's written, it's the direction from 1 to the vector Z, not to the point Z. This is the vector from negative 1, because it's got to be Z minus Z1. This is the vector from negative I, to Z. Right. The direction is the same, therefore P is on the outside. We can also say, therefore, can't we say that, so then that equals that, can't we say that AP is parallel to vector BP? Would you agree? Do you think AP is parallel to BP? If the argument's the same. We're trying to find the Cartesian equation of that line. So what I'm trying to say is that the gradient of BP equals the gradient of AP, because the direction from the real axis is the same. I'm trying to say A, B and P are collinear to try to find the equation of the line. So the vector AP will be parallel to vector BP. Therefore, because B is a common point, A, B and P are collinear. And we know that P lies outside, of course, of AB, as AP and BP are in the same direction. So P lies outside, so that AP and BP will be in the same direction, okay? Therefore, what's your Cartesian equation? What do you think the gradient of that line is?
1.
Yeah, it's 1. And look, negative I is the point negative 1, really. Do you know what I mean? This is the point 0, negative 1. I know it's the vector. I know it's the represents the complex number negative I. So what's the equation of that line? Isn't it y equals positive gradient is 1, x what? Minus 1. That's the Cartesian equation. Y equals x minus 1. Wait a sec. But it's not defined in the middle. For values of x, what? Less than? Yeah. It's only solid down here and up there. It doesn't include the middle bit. So the Cartesian equation is y equals x minus 1 for values of x less than 0 and x greater than 1. In other words, it doesn't include the x values from 0 to 1. Okay, for values of x less than 0 and x greater than 1, or you can put except for 0. Remember, you can't include 0 and 1 as well. You've got the open circles. Okay? Now, we've still got 2 more. And then there's the example from the textbook, which is page 45. Z is a complex number which satisfies these inequalities. Tell me what that first one means. What is it? You've got a circle with centre what?
0, 3.
0 minus 3. Yep, radius on this side 3. Circle with centre negative 3, 0, radius 2, and you're shading in between. It's an annulus. All right? It's part of an annulus because of this argument. And the argument of Z, so also the argument of Z plus 3 lies between 0 and 60 degrees. So let's do our circle first. So -1, -2, -3. So I'm going to write up all the inequalities. I'm not going to write them up as inequalities. I'm writing them up as formulas. Actually, I'm going to go like this. Z plus 3 equals 3. Got it? This is what we're drawing. Z plus 3 equals 2. Got that? Modulus. That's what we're sketching. Modulus of Z plus 3 is 3. Modulus of Z plus 3 is 2. I should really be writing that as Z minus -3 is 3. Z minus -3 is 2. And the argument is from 0 to, and the argument of Z minus -3 is between 0 and 60. So let's do the argument first. So drawing a little circle here, about 60 degrees. Do I do solid or dotted lines? Solid, solid, solid. Okay, I'm not shading yet, but I know it's going to be in between, yeah? Then I've got my circle with center -3, radius 2. Solid or dotted? Okay. So if the radius is -2, then it must come out to -1. And the radius of this other one is 3, so it must come all the way to 0. So this is an annulus. See, these two are telling me I've got an annulus. I'm not drawing the whole thing. I can continue them. I'll continue them with dotted lines. But the argument is just from 0 to 60 degrees. But the argument starts from -3. Z is -3 on the x-axis. I'm going to call this point A. Remember, this is the argument from the point -3. So that's what Z plus 3 is, Z minus -3. Okay, so where do I shade? Where do you think? So the argument means all of it, but the other one is the region between here. So I shade. So I want, the argument's telling me to shade all of that, but the annulus is telling me, this is telling me to shade just between the two circles. That's it, I just go here, only from 0 to pi on 3. So that angle there is pi on 3. The first circle has a radius of 2, the second one has a radius of 3. You're shading between those two circles. See here, you've got to be really careful. You put the -3, you note that this is -1, that this is cutting here at 0. I don't need the open circle, like there normally would be an open circle there, but I'm shading over here, so the open circle is irrelevant now. Got it? So Z is the complex number which satisfies those two regions. Notice and means intersection of those regions. It says find the area and perimeter of the region on the Argand diagram determined by these restrictions. So I'm just going to, all right, area. Let's do the area. Isn't it the area of, isn't it theta? Yeah, 60 over 360, which is 1/6 times pi squared minus, so we can just write it as 60 over 360 is 1/6 of the circle, isn't it? Pi, annulus, do you know how an annulus is r squared minus r squared? I can do the big circle, 1/6 of the big circle minus 1/6 of the small circle. So I don't have to write it like that. I can just go 1/6 pi r squared minus 1/6 pi little r squared. Got it? 1/6 of pi r squared minus 1/6 of small pi r squared. Are we okay with that? So now I'll go 1/6 pi bracket r squared minus r squared. I'll go common factor. You're okay with the 1/6 because 60 over 360 is 1/6. Okay? So I've got 1/6 pi times, what do we got? 3 squared minus 2 squared? Yep, so it's 5 pi on 6 units squared. And the perimeter, haven't we got one perimeter? You've actually got the 2 straight bits and the 2 curved bits. What's the length of this straight bit?
kind of the same thing.
Yeah, it's 1/6 times 2 pi big R plus 1/6 times 2 pi the little r plus, so that gives me this distance and that distance plus 1 plus 1. Plus that bit is 1 unit, same as that bit, 1 unit. So it's 1/6 times 2 pi times 3 plus 1/6 times 2 pi times 2 plus 2. What do we got? Isn't that pi? First one, 1/6 of that plus 1/6 of that. So what do we got? Pi plus 2/3 pi plus 2. Common denominator? 3, 5 pi on 3. Because it's 1 2/3. Or it's 3 pi on 3 plus 2 pi on 3. 1 2/3 is 5 over 3 as an improper fraction. 5 pi on 3 plus 2. I'm not putting the 2 with a common, and that one's just units, not units squared. Okay, now, next one. Oh, this is the fun one. And I'm going to need all the time to do this. This is fun because it's a 45-degree rotation. It's not, you know, plus pi is easy. They're exact opposites of each other. But plus pi on 4 is a 45-degree rotation. Now, we need to concentrate. So haven't we got, I'm going to let A be the point 1, 0. And then that's going to represent Z minus 1, okay? I'm going to let B be the point. You know how this is arg Z plus 1? Isn't that Z minus negative 1? So just under here, I'm just going to write arg of Z minus 1 equals arg. This is what it means, Z minus negative 1 plus pi on 4. So I'm going to let B be the point. That's going to be the point negative 1, 0. And that's going to represent the complex number Z plus 1. Now, you know what this is telling me? That the direction, if I look at that, the direction from 1 to my complex number is the same as the direction of negative 1 to the complex number plus 45 degrees. So I've got to do the direction from the complex number direction from negative 1 to my complex number. If I add 45 degrees onto that, I will get the same direction as the direction from 1 to the complex number. Okay, so let's just sketch where A and B are. So therefore, I'm just going to put that AP will happen to be, if A is that, I should put that AP, represents Z minus 1, And what's wrong with me? If A is that, look, you're going to have no stuff yet left. AP will be Z minus 1 and BP will be Z plus 1. That's what I meant to say. Okay, sketching. We're going to need 2 diagrams because we've got 2 cases that we need to consider. And I would use pencil and pencil only here. And I think I better do the same for myself. So, see this situation up here? Arg of Z minus 1 equals arg of Z plus 1 plus pi on 4. This is what it requires. So requires, remember how this one's the vector AP equals the vector BP plus pi on 4. That's what we're saying. Because arg of, what that means in everyday language is that the vector AP equals the vector BP plus a rotation, an anti-clockwise rotation of pi on 4. That's what that means. Arg of Z minus 1 equals arg of Z plus 1 plus pi on 4. If I let this first Z minus 1 be AP, then AP is BP plus an anti-clockwise rotation, of pi on 4. Okay. I shouldn't put plus with an anti-clockwise rotation of pi on 4. All right, let's draw where A and B are. A is 1, 0, and B is negative 1, 0. Now we've got two choices. Either P is up the top or it's down the bottom of the line. See, P is either going to be up here or down there. So let's look at P down here first. Now it doesn't matter where I put it. I'm just going to put it here somewhere. I might put it down here. I'm going to put it down there. Okay, let's draw AP. So with your pencil, I want you to draw AP. That's AP. And then I'm going to draw BP. Now what I'm going to do, so I've got AP, BP. I'm going to draw a dotted line representing the same direction as AP as well. Now, if AP is there, oh geez, let me put these points above the line. Sorry, I've got to get you another. I've got a few of these on my desk. I'm using up your whole thing. All right, so if this is AP, this is the arg, this is the arg of Z minus 1. Now, does that equal the arg of, and this here is the arg of Z plus 1. Now, is arg of Z1 plus pi on 4? Well, if I take that argument and go plus pi on 4, isn't it here somewhere? If I take this argument and go plus pi on 4, aren't positive angles that way? Then AP should be up there somewhere, but it's not. So this doesn't work. See, look, if I've got, say, P here, and it doesn't matter whether I put P there or there or there, it'll be the same. So I draw AP. This is also AP, same direction, all right? I need to be able to take BP and rotate it anti-clockwise pi on 4. See, if that's there and that's there, I actually have to rotate it clockwise to get to the same direction as AP. So here's BP. Only if I rotate clockwise will I get the same direction as AP. So that's wrong. That is actually this. If I put P down here, it's actually arg of Z minus 1 equals arg of Z plus 1 minus pi on 4, because negative angles go down. So P's got to be above the line. See, actually, if I look at this, here we go. If P lies below the x-axis, then the arg of Z minus 1 equals the arg of Z plus 1 minus pi on 4. See? All right, so I've drawn AP and I've drawn BP, and I'm drawing this dotted vector here parallel to AP. So if I take BP, see, I want AP to be BP with anti-clockwise rotation of pi on 4. So I'm supposed to be able to take BP, rotate it anti-clockwise pi on 4 and get AP, but I don't. I've got BP, rotated pi on 4 clockwise to get AP, same direction as AP. So therefore, if P lies below the x-axis, then I've got the minus pi on 4 situation. So therefore, P must lies above the x-axis. So look, you've got two guesses, below or above. If you guess the wrong one first, then the other one's going to be right. So now I'm going to put A there, B here again. Let's say P goes up the top. It doesn't matter where it is. I'll just stick it there. So here is AP. I'm going to draw this one parallel to AP. All right. And here is BP. Now, I know that doesn't. So this is BP. So it does AP equal BP plus a 45-degree rotation? Look, it doesn't matter. I'm only drawing it. I'm trying to draw it roughly 45. I think it does. Look, if you take BP there and rotate anti-clockwise 45, you get the same direction as AP. So from this, we can see that AP is the same as BP plus 45. So therefore, what does AP represent? Therefore, I can say that arg of Z minus 1 equals arg of Z plus 1 plus pi on 4. Sorry, yeah, plus pi on 4.
Are these just theory or like are these
These are actual questions. These are examples from
so
Cambridge.
you can get these questions
Oh
and
yeah,
then
you can
just
get
say-
questions like this.
Negative.
Well, you could.
So how do we answer this?
Just what I'm doing.
Oh.
Yeah, this is how you answer it. Yeah, these are questions. So these are questions. Sketch the curve in the Argand diagram determined by that and find its Cartesian equation. We're still nowhere near finished. So what we're trying to do is we're just trying to see if P lies above the line or below the line. We're just trying to interpret what this means. Do you think we're sort of getting the idea of this vector plus pi and 4 should give me the same direction as that vector? That's what that means, okay? So we've got, therefore, that P lies above the line. So, you know, because we've got, because of alternate angles as well, just one sec. With P being up here, that it's BP plus a anti-clockwise rotation of pi and 4 gives you the same direction as AP. Got it? Now, because I drew this line parallel to AP, then by alternate angles, this angle here is pi and 4. So I'm going to go, since alternate angles are equal on parallel lines, then angle BPA equals pi on 4. So therefore, P, you're going to ask me now why, lies on the major arc of the circle, just wait, I'll explain it in a minute, through A and B. Major arc AB. Oh, no. I don't think, oh yeah, are A and B on the circle? I don't know about that. One sec. Because P could be, say, here. P could be there. P could be there. P could be there. And these are angles at the circumference. I know my thing doesn't look like a circle, all right? Angles at the circumference subtended by the same arc are equal. So therefore, P lies there. We're going to go over the page. I'll just show it to you here. So you can actually, if I just explain this, you can then copy it at home, all right? So just looking at whatever, 24, 34, I don't know how many minutes. So you know how we've just done that? I've got point A at 1, 0 and point B at negative 1, 0. We know that P lies somewhere along here. I've just gone and thrown it at the top, but it could be there. We know that this is pi and 4. You know how the angle at the centre is twice the angle at the circumference subtended by the same arc? So if I just happen to come here along the y-axis, just for convenience, I know that this is pi and 4 up there. Therefore, this angle in the centre here is 90. Because these are equal radii of a circle, and this happens to be the centre of the circle, then I have an isosceles triangle. Because isosceles triangles have symmetry, you know, that angle equals that. These are right angles. This angle there equals that angle there. So if that's 90 and these two angles here are equal, if that's my y-axis, then this is pi on 4 and that's also pi on 4. They're both 45 because that's 90 in the middle. So now the centre C of this circle lies on the perpendicular bisector of A and B, okay? And chord AB subtends an angle of pi on 2 at the centre, you know, angle at the centre. Angle at centre is twice angle at circumference, subtended by the same arc, all right? So therefore we've got an isosceles triangle. If this is pi on 4 here, isn't this pi on 4 there? Isn't this an isosceles triangle? If this is the point negative 1, 0, so if that's 1 unit across, this must be 1 unit up. Because look, we've got right angle, 45, 45, isosceles, 1, 1. This hypotenuse, if I call it x, is root 2. So I can do it that way by angles, or I could have just said, what have I done here? X squared plus x squared is 2 squared. What's that? I think I've made a mistake there. Yeah. Look, I'd like to go 1 squared plus 1 squared is, why don't we just go x is the square root of 1 squared plus 1 squared? I think that's easier. Where did I get that from? I don't know where I got that from. I reckon we just do, here, we just do it like this, that 1 squared plus 1 squared is, I got it last night and I forgot what I did. How do we know?
Yeah. Because if you're saying
Because P is a point that can move, it's because angle at the circumference subtended by the same arc.
so you're assuming it's a circle first, or you already know it's a circle.
It's got to be. It's because, you know how I did that alternate angle thing here? Because this angle will always be pi on 4, then that's how we know it's a circle.
No, doesn't that
I'm not assuming it's a circle. It's because we
so let's
keep...
prove it's a circle first.
Yeah, well, you're trying to find the equation of the locus of P. And because this angle is always going to be pi on 4, we know that through circle geometry that angles at the circumference subtended by the same arc are equal. So therefore that makes it a circle. Okay? All right, and then because angle at centre is twice angle at circumference, we've got a right angle. You can go one across. We know that because of the symmetry of the equilateral triangle, that this has got to be 1, that's got to be 1. This is therefore the square root of 2. Okay? So therefore is x squared, so x is the square root of 2. So therefore you've got a circle with centre. So therefore we've got a circle, what do we got? Circle, centre 0, 1. Radius,
How come the radius?
because root 2. Because that's how you write it, as x squared plus is r squared. That's the equation. So you know how, so if the centre is 0, 1, you go, the formula is x minus h squared plus y minus k squared equals r squared. And r is root 2. So it equals root 2 squared, which is 2. Now, I've got for y greater than 0, meaning you've just got the major arc above.
C is the centre, right?
Yeah.
And A is 1, 0. So if it's the distance from C to A is 1, 0.
Yeah, no. From there to there is 1, and from there to there is 1. Oh, I know.
No,
You.
but your
Oh,
coordinates, it's just the distance.
But-
Your C is the centre 0, 1.
because I've worked out that that is an isosceles triangle. Because if that whole thing in the middle is 90, by the symmetry of an isosceles triangle, if this is 90, because an isosceles triangle has an axis of symmetry down the middle, that's 45 and that's 45. So therefore, if that's 90, that's got to be 45. So if that's 1, that's got to be 1, because you've got an isosceles triangle.
So why is the coordinates 0, 1 for C and A 1, 0? Shouldn't it be root 2, 0 then? For C.
No, because the hypotenuse is root 2.
Then that means the distance from C to A would be root 2. So the coordinates would be root
Look,
2,
the-
0.
No, root 2 from there to there, root 2 from there to there. Root 2 is about 1.7. Root 2.
No, like the coordinate. You wrote C
Is
0,
0.
1,
It is 0, 1.
and then you wrote A is 1, 0. So the distance.
That's right.
The distance is. Oh, wait, never mind. I get it.
Yeah. A is 1, 0. C is 0, 1.
Yeah.
So you've got a right angle triangle with 1, 1. That's the square root of 1 squared plus 1 squared is root 2. If it was a 60-degree angle, they'd all be 1. Yeah? Sure? All right. Okay, what I'll do, there's another question like this, example 20 or something in your textbook. So I will, similar thing, does P lie above the line? Does it lie below the line? Arg of Z minus 2 over Z plus 2 is pi on 2. So I'll continue with that example. Can you also let me know of your problems, please? Email me and I can do some video solutions if you require that. So it's a catch up. We want to be finished 1.4 by next week. All the work.
I'll do 1.4 by time.
Yes, because we've done all the theory for 1.4 now. Okay.